Okay, let's finish our calculus review. So I have to use the definition of the derivative, limit. So that means the derivative is limit f of x plus h minus f of x over h. So h goes to 0. And so over here, my scratch work, I say, what is x plus h? Well, it's square root of x plus h minus 1. And so its limit as h goes to 0 of what? Itchy. Square root of 2x plus h minus 1 minus square root of 2x minus 1 all over h. So I now evaluate that limit, and I notice when I let h go to 0, I end up getting 0 over 0, so that means I need to remove a whole, and the way that we do that is by using the conjugate. So square root minus square root over h. So I go to, actually not over h, excuse me. I end up using the exact same terms, but a different middle sign. So x plus h minus 1, 2x minus 1, square root 2x plus h minus 1, 2x minus 1. What that gives me is this limit, but then it's the first one squared minus the second one gets squared all over h times square root 2x plus h minus 1 plus square root of 2x minus 1. So why is that wonderful? Because these cancel out. And then really what this is 2x plus 2h. So one of these cancel out. So that's gone, this is gone, this is gone, this is gone, that's gone, that's gone. All that's left on top is 2h. That makes me happy because there's an h on bottom. And so if I can factor out that h from the top and the bottom, I'd be left with a 2 on top and a square root 2x plus h minus 1, 2x minus 1, limit h goes to 0. These cancel out beautifully, and I get limit h goes to 0 of 2 over root 2x plus h minus 1 plus square root 2x minus 1. Then you just let h go to 0, and you get 2 over, and you get 2 of these things, square root of 2x minus 1. These cancel, and your answer is 1 over square root 2x minus 1. Right? Okay, notice it says using the definition. Be careful on the exam. Graph, sketch the graph of f prime on the same axes. Well, here we see the derivative is 0. That's where we usually like to start. Here's a small positive, an even bigger positive, and an infinite positive. So there's going to be a vertical asymptote here. So it's going to do that. On this side, I've got a small negative, an even bigger negative, then an infinite negative. So over here, it goes down like so. So we have these two vertical asymptotes and that graph. Over here, I've got a big, small negative, whatever, bigger negative, huge negative, infinite negative, right? So it seems like it goes like this over here. And then as it's going out this way, it looks like it might be getting closer to 0. Then on the other side, looks like it's a big positive, even bigger positive, huge positive, huge positive. So it looks like it's doing this on this side, right? All right. Then differentiate the function. Notice anytime we can simplify first, we want to. So we know that a plus b over c is a over c, b over c added together. So I'm going to take it, and since I have 3 things added together over 2x, I'm going to do each of them over 2x and then add. So 2x to the 1/2 and 3. That simplifies to 2 plus x to the negative 1/2 plus 3/2 x to the negative 1. So now I'm ready to differentiate, and I get negative 1/2 x to the negative 3/2, negative 3/2 x to the negative 2nd. So then we don't like negative exponents. So it's this minus this. Again, differentiate but do not simplify. When I look at this, its form is stuff over stuff. So that means its derivative is low d high minus high d low over low gets squared. So it's going to be low, high, high, low over low gets squared. Low derivative high is 6t minus low d high minus high, high d low. Well, the form of this thing is stuff times stuff. So inside of here, we're going to get first, derivative second, plus second, then the derivative first is just 1. So that is what it would be without any simplification. Here it says let p of x equal this times this and find out what p prime at 0 is. Well, if you want to know p prime and we're taking the derivative of a product, it's going to be the product rule. First derivative second plus second derivative first. Now, if you want to know what happens at 0, you just plug in 0. So it's this plus this. And so f of 0 is 4 times g prime at 0 is 1 plus g of 0 is negative 2. F prime of 0 is negative 3. So it ends up being 10. Here, find the limit or show that it does not exist. If we let, here you see it's going to go to 2, but let's see why. Well, why do I know it's going to 2? Because this is the leading term, and that's the leading term. So in the long run, these are going to be the terms that dominate. And that's why I can see it's going to be 2. But to really show it, I use that 1 over the highest power on the top and the bottom. When we do, on top, we get this. On the bottom, we get this, right? But x is equal to the square root of x squared if x is greater than or equal to 0. And that is the case because we're going to positive infinity. So we end up getting, what is this? The limit as x goes to infinity. And I end up getting, what, 10 plus 1 over x. And here I get 25 x squared over x squared minus 2x over x squared plus 3 over x squared. Because I use this idea and bring it all under a square root x squared, right? Then we just let x get really big. Well, this is 25, so it stays that way. This goes to 0 and this goes to 0. And so you end up getting, oh yeah, and on top, this goes to 0. So on top, we end up getting 10. On bottom, we end up getting the square root of 25. So it's 10 over 5, which is 2. Okay. Here, you notice we get infinity minus infinity, which makes no sense. So we have to multiply it by the conjugate. Boop, boop. So we're going to do plus square root then limit x goes to infinity. On top, so this is just over 1. On top, we're going to get what? The first one squared minus the second one squared all over the bottom, right? So what happens? These cancel out beautifully, and we just end up getting a positive 311 on top. This is the limit as x goes to infinity. And on the bottom, we have x squared plus the cube root of what? X to the fourth minus 311. So in the long run, as x gets really big, this thing simply goes to 0. Right? All right. This one here, again, it's one of these 1 over the highest power things. So it's 1 over x to the fifth on top and bottom. So very quickly, we see that this turns out to be 20 minus 7 over x squared. And what? 2 over x to the fourth plus 9 over x cubed plus 5. That goes to 0, that goes to 0, that goes to 0. So we simply get 20 over 5, which is 4. So I can make this function as close to 4 as you want to by taking x sufficiently large. Here, find the equation of the tangent line to the curve. Y minus y1 is equal to m. X minus x1. This is your x1, y1. So my y1's 4. My x1 is 1. Okay. Let's see. Okay, so now what? Now m is just the derivative at my x1. So in other words, it's the derivative at 1. But, and it's not the derivative of f, it's the derivative of g. But g prime is just equal to 10x plus 2. So m is equal to g prime at 1 is equal to 12. So that means y minus 4 is equal to 12, x minus 1, and we're done. Find the limit. Well, this is a case where we know that the limit as x goes to 0 of the sine of x over x wants to be 1, right? Because these go towards each other. Well, the closer you get towards 0, they really want to be the same. So I wish it was pi x on the bottom. So I wish that 2 wasn't there, so I put a 2 on top. So to put a pi on the bottom, I must also put a pi on top. And to put a 2 on the top, must also put a 2 on the bottom. So this ends up being this times... wait. Okay, hold that thought. Let me do that one more time. So what we do is we pull out the 2. So I've got a 1/2 on the outside. Are you happy with that? So now I have sine of pi x over x. So I can pull a constant through a limit as long as the limit exists. So we're good so far. Well, then I say, look, I wish that this was pi x on the bottom. But you cannot just simply put a pi on the bottom. You must use a well-chosen 1 and also put that pi on the top. But again, if this limit exists, then I can also pull that constant out, which I do. So I put it there. So this, if you let theta equal to pi x, do you agree that as x goes to 0, theta actually goes to 0? So what you have is pi over 2, the limit as theta goes to 0 of the sine of theta over theta, but we said that that was equal to 1. So we just get pi over 2, because that's all going to 1. Here, explain what this means in words. It means that the cosine of pi x over 2x can be made as close to negative 1/2 as desired by taking x sufficiently close to 1. And that's that. Is that the whole thing? Yeah, man, that's the whole thing. So the rest of this is just another version of the same thing. Okay? Oh, well, I'll be nice and do another version if that makes you happy. since I'm already doing it. Find the equation of the tangent line. Y minus y1 is equal to m x minus x1. So this is x1, y1. This is y minus y1 is equal to m x minus x1. But m is just the derivative at x1. In this case, it's the derivative at 1. But the derivative is 14x plus 2. So g prime at 1 is equal to 16. So this is equal to 16x minus 1. And we're done. Here, find the derivative using the definition of the derivative. So it's going to be it's going to be the limit as h goes to 0 of f of x plus h minus f of x all over h, but f of x plus h in this case is 1 over x plus h plus 1. So this is going to be 1 over x plus h plus 1 minus 1 over x plus 1 all over h. Well, one thing that makes this easier is instead of dividing by h, let me just visually pull out the 1 over h, and it very quickly looks a lot nicer. So if I do that, I now have this minus this. But now I want to get a common denominator. So I hit this with x plus h plus 1 on top and bottom. That's going to be my well-chosen one. Over here, x plus 1 on top and bottom. If you do that, what you get is limit h goes to 0, 1 over h, x plus 1 minus x plus h plus 1, all over the common denominator of this times this. Why is that great? Because that and that cancel out, leaving only negative h on top. But that negative h and this h cancel out. Well, let me be careful so that you can see it. Well, that means that I've got 1 over h. There's only a minus h left on top, and a this on bottom. So now I can clearly see that when these cancel out, it leaves a negative 1 on top, and it leaves an x plus h plus 1, x plus 1, and now you let h actually go to 0, and you get negative 1 over x plus 1, God squared. Cool. All right, here, 1 over highest power, 1 over highest power. That's what we do when we see that we're going to infinity. That's a common technique. So we get 14 plus 1 over x on top. Again, we say that this is equal to this since x is going to infinity. In other words, since x is greater than 0. So that means on the bottom, I really get 49 plus 2 over x plus 5 over x squared. So as x gets large, that goes to 0, that goes to 0, and that goes to 0. So you just get 14 over the square root of 49, which is 14 over 7, which is dose. Okay. Here I do 1 over highest power, 1 over highest power. A technique for if we're going to infinity. So I get 30 minus 7 over x, 2x cubed, 9 over x squared plus 6. And if you let x get big and you have a constant over getting big, it goes to 0 and you end up having 5. Here, I think we've already shown this on the other one. This ends up going to 0. So see the other part of the video. Here, if we sketch the derivative, it looks like this derivative is negative 1. So it's negative 1 down here, and it doesn't exist. Over here, it looks like it's 1. So over here, it's 1. Yep. And then this is the same one from the other video. The one that's 0 goes up to positive infinity, goes down to negative infinity. Okay. This and this I've already done. You can already see those on the other part of the video. This looks exactly the same. And this are very similar, except for just changing in a constant. So great work. Happy studying. Bloop, bloop.